In this part of the AlphaZero for Connect 4 series, we'll be building out the brain of the algorithm. So in the past videos, we've built out the game environment so we can actually play Connect 4 in Python code. We then moved on to the Monte Carlo tree searching process, which will aid in the decision-making portion of the game. Basically, throughout our training process, we want to be able to simulate games in Connect 4, and the Monte Carlo tree search is kind of one half of that decision-making process, so that we can place a piece on the board in any given one of those simulations. The second half of that is the neural network model that aids in evaluating the board state and actually guiding the tree searching process. So this network will be able to tell, is a given board state valuable for either the players, and what is the best action that it thinks the player should take from that position. So the model will be built out in PyTorch. It'll be a ResNet architecture. ResNets, without getting into too many details, have been very well known for image classification tasks. So these are just basically layer after layer of convolutions, and then there is kind of one specific breakthrough that we'll talk about as we start building it out. That is kind of the revolution of ResNets in the first place and why they became so valuable for image classification. And why would we want to use a model for image classification for a board game? Well, as you can think about, an image is actually very similar to a board game in many ways. We basically have this two-dimensional array of pixels, which is, in our case, a two-dimensional array of pieces on a board. And then we actually have also channels to the image. So in image classification, we typically have a red, green, and blue channel to a colored image. In our case, we have also three channels to this board, which is telling the model, the first of the channels being player one's pieces, second being empty spaces, and the third being player minus one's pieces. So it's actually a very similar structure of input data that we'll be using as in an image classification task. We can jump right into it. So we'll be using, I think I mentioned PyTorch to this. We can start importing some of our libraries. We can import torch to start. We can import torch.nn as an n. And we'll also import functional as f. These are kind of standard naming conventions for these torch packages if you're not familiar. And then we will also need NumPy. So the first thing we'll need to do here is just define our class, which we'll call Connect4Model. And we will pass nn.module so that we can inherit from here. And this is basically, in any definition of a PyTorch model, this is in 90-some% of cases, this is the way it'll start. Right? So we're going to define our class, our model class, and we'll inherit from the module, nn.module from PyTorch. From here, we can define our init method. Under this init method is where we'll basically initialize all the layers of our network. And let me actually zoom a bit here. So we'll pass self, and then the only other parameter we need here is the device. In our case, we'll be running this on a GPU, so we can get into how exactly we define that device in a future video, but we'll be basically just passing that device and then initializing an attribute here with that device. So another thing we'll need is to be able to call from nn.module. We'll also need this super in it. So we're basically just initializing everything from nn.module, and this is very, very standard way to basically start creating any model in PyTorch. So a few different components. We can kind of just define out our model architecture before we actually get into the layers. So we'll have this forward function, again very standard, and the way I like to think about this is, so our forward pass through the network will just take in our input data which in our case will be the state of the board. We'll just call that X. But the way I like to think about this is in the forward method, this is defining the connections between the layers. Well, in this init method here, we need to define the layers themselves. So we'll start by just initializing. We'll pull from the torch libraries and just basically tell the model or tell PyTorch what are the layers we're going to be using. And then in this forward method, we'll be defining how are they actually connected together. So the way we'll do this, and this is coming pretty much straight from the paper that we outlined in the intro to this series, except for modifications obviously because we're playing a different board game. But they basically will start with a convolutional layer. From there, we will start with, we'll go to one of our first res block is what we'll call it. This is basically two convolutional layers with, one kind of caveat, which is the breakthrough of the ResNet, which we'll talk about as we start defining those layers. In this video, we'll just start by defining two res blocks. I think in the case of AlphaGo, they used 13 or 12 or 13 it was, and we probably don't need that many. We might end up using more than two, but I think just for example purposes, we'll start here. The reason I say we might not need that many is because obviously Connect 4 is first a smaller board and probably also a much less complicated game than Go in the first place. So I'll just assume that we need a smaller model to begin with. And then one interesting thing about how this model is defined is we will initialize a value head and also a policy head. And I may have touched on this in our past videos a bit, but basically the value head evaluates it'll output a number from -1 to +1. What is the value of this state of the board from player 1's perspective? So if player 1 is about to lose, this should be -1, and if player 1 is about to win, this should be close to +1. And the policy, this is what is actually giving you your actions between, from 0 to 6, or it's telling you which column is the best next action to play on the board. And again, we'll touch on that a bit more, but let's get into kind of what these layers look like. So we'll start out with this convolutional layer, and we'll call this just initial conv, and we will pull this function conv2d from this NN module, and we can open up the PyTorch documentation here, and let's just search for what parameters do we need to pass into conv2d. So in the documentation, we can see that this takes in, let's just copy and paste all of these parameters. Some of them we won't use. But basically we need to specify the number of in channels. We already said that this is 3 in our case, just like it is with an image. We have 3 channels to so we're basically passing 3 boards to the network. As I mentioned, one from player 1, telling it where player 1's pieces are, another layer is telling it where the empty pieces are, and a third telling it where the opponent's pieces are. The out channels, this is basically, it's an arbitrary choice, but it's defining the size of our network. In the paper we're trying to mimic here, they used 128 was, I believe, the best version of this model. And then the kernel size they use, or this is also known as the filter size, they used a 3x3 kernel for this layer, or for the initial layer, and a stride of 1. So just going through these one by one here, we mentioned the kernel size is the size of the filter. So we're not going to get too far into the details of what a convolutional layer is actually doing. But basically this is a small window that is going to pan over the board, and it's going to do some sort of computation on that section of the board. and it's gonna go, from top left to bottom right. It's gonna go over the entire board, and it's gonna be this 3x3 window that's looking at every little quadrant, or I guess 3x3 set of the board. The stride is just telling the network how many spaces to move over when it's going through that convolution. So it doesn't make sense to do anything other than 1 in the case of a board game, because obviously we want it to look at every piece on the board. So we'll use a stride of 1. The dilation we won't discuss. You can delete that. Groups we won't discuss. The bias is mentioned in the paper. Probably won't talk about the details here, but for this layer they did use a bias of true. And then, so the last thing to discuss will be the padding. So in any convolutional neural network, as I mentioned, that filter is going to pass over the board, and basically we want to make sure that after our convolutional layers, the board continues to stay the same size, so that we can add as many res blocks as we want, and so that the data that we're passing through the network isn't getting smaller and smaller as we go. So, and the reason this would happen, I'll actually put a link to a resource that explains kind of the convolutions a little bit better, since I don't want to spend too much time explaining it. But basically, we want to kind of pad zeros around the edge of the board, so that when we convolve it back down, we get back to that 6x7 board. So by entering padding 1 here, we're basically going to have a 7x8 board, or actually, we're going to add zeros on all sides of it. So it would then be an 8x9 board, and then we're going to convolve it back down to a 6x7 board. And again, the link I'll provide in the description will explain why that is exactly the case. But this is also a default parameter, so we won't include it here. But we're going to basically add zeros around the edges and then convolve it back down to a 6x7. Okay, so after all of our convolutional layers, we are going to add a batch norm layer. This is pretty standard practice with the ResNet. So we'll call this initial batch norm. I believe it's, what is it called? Batch norm 2D. And this will just take our number of features. This basically doesn't change the shape of the network at all. It's just batch normalization. Again, not going to get too far into the details here. But we will keep this to be 128. This is the input from the previous layer. And so this is kind of the structure of all of our convolutional layers. So I'll copy this, and we will basically modify this to create our first res block. So now that we have outputted 128 features here, we can change our input here to accept 128. Again, this is basically, we're keeping the board 6x7, except now these are the channels that we're outputting from this, from each of those neurons. We're going to keep it 128, and again, our padding is going to allow us to maintain that sizing, and we're going to have basically 2 sets of this same structure. So remember, in this part where we're just initializing all these layers, we don't actually need to specify any of the connections, and so this is just going to look like a standard convolutional neural network from here, and not a ResNet. But once we actually get to the forward function, we will kind of get to the magic of what the ResNet is actually doing. Okay, so this we'll call res1 conv1, and call this here okay, so we have our first res block, and actually another thing to note about these res blocks is we're going to change our bias to be false. This is what was done in the case of AlphaGo, so that's what we're going to do here. but they adjust this bias parameter. As I understand, the batch norm layer actually does a similar thing as when we have bias true here, so it's sort of trivial in the first place to actually set this to true right before a batch norm layer. But you know, in the name of trying to you know, recreate AlphaGo in this case, we're gonna use the same parameters as they did. Okay, so we're gonna have this is basically now a block of layers that we can basically add as many of these as we want, right? Because the input to this block is the same as the output, or you know, the same shape as the output, and we can now just recreate this layer over and over again. And I think we'll do something on the order of probably 5 to 7 or 8 of these in practice, and that will be a hyperparameter that we can tune throughout the process. For now, let's just do these 2. And if there's any deep learning experts watching this video, I'm sure you're cringing at the way that I am actually defining these layers, just because you know, it's very tedious to name them in this way. There's a much more conventional way to do this. I'm doing this so that it's very easy to understand for the viewer and to actually see all the layers we're doing. But maybe in a future video, I'll show how you can actually use kind of meta programming techniques to just define these all. We can separate this res block out into a separate class, and then basically just initialize it here within a for loop using some like a kind of a meta programming technique. But if you don't understand what that means, you know, that's exactly why I'm representing it this way for now. So we will maybe get to that in a future video. So then finally we get to basically the value and policy head of our network. So here we need, we're going to start with a convolutional layer, so I'll call this value conv. And we can copy again from here. So we're going to start both the value and the policy head with convolution. And again, I'll pull up the paper we're trying to mimic on, I believe it's on page 8 here. So they have this section here on the neural network architecture. Basically, they say that they're using a kernel size of 3 by 3 with stride 1 for their main hidden layers, and then once they get to the last layer before the value and the policy head, they bump that down to a filter of 1, or a kernel size of 1 by 1 with stride of 1 as well. And in the value network, they use a hyperbolic tangent activation function. Okay, so we will, again, kind of arbitrarily, we're just trying to basically distill this down before we bring it into the value head, which obviously is just 1 neuron. So we'll go down to 3 here and set our kernel size to 1, as that's what they did in the paper, and we no longer need this this padding parameter. So the padding can just be 0 now in this case, and the shapes will all work out that way. I believe they also mentioned the bias. I think they set this back to true here. Yeah, so in this last layer, the final layer convolves the one filter with a different bias for each position. So they did use bias in these last layers as well. Okay, so this will be what we use for our value head, and then we'll bring this into first we can call this value fully connected. Maybe we can just bring this down to like a 32 neuron layer. Again, we're just trying to kind of downsize the data into that final neuron. So we can expect an, first we should batch norm this. So we should expect our output size of 3. And we can call this value batch norm. We basically want to specify an input for every piece of data in this output here, right? So because this is a fully connected layer, so now we just need basically one neuron for every number in the output of this batch norm layer. So what that's going to be is that's going to be our out channels, which is 3. We're back to like a normal board here, I guess. So we specified that we have 3 channels of output here, which means we're basically back down to the same exact board size as what we started with, right? We have 3 channels, 6 rows, and 7 columns. So that will be the input, or the number of inputs here, 3 times 6 times 7. And the number of outputs, as I said, we can just specify 32. So this is like what you would call the number of neurons in the layer. We're going to expect 32 outputs coming into the final value neuron, or what we'll call the value head. So we'll just call this the value head. And we'll do the same thing. And we'll just have, like I said, just one neuron in that final value head. We don't need to define our hyperbolic tangent function just yet. We can actually just call that straight from this functional library once we do our forward pass. I'm not sure how PyTorch really decides which activation functions are a layer themselves and which are just called by functional. But as you'll see, some of them are actually within the layers library, interestingly. So we will do a similar thing with this layer, except we're going to just go straight, because we're not trying to bring it all the way down to 1 neuron now. We want to actually output 7 neurons in the final output, because this is the policy of the network being able to actually make an action on the board. So we want 1 neuron per column on the board. If column, basically if neuron 4 fires, or is basically the maximum output of the network, that means that the network thinks that column 4 is the best move based on this state of the board and which player's turn it currently is. So we will do the same sort of convolution down here. And then we can batch norm. We go straight to our 32 here. Like we specified our 32 output size, and then we'll go straight to the policy head next. So this will be another just linear. By the way, linear is the function that you call from PyTorch to just, this is just a regular, what you call a fully connected or dense layer in some other contexts. But it's the same meaning. And here, in the same way we did 3 by 6 by 7, we now have 32 by 6 by 7 with the output channels from the last layer. And then we want the output channels of this layer to be 7 neurons, like we mentioned. And as I said before, some of these activation functions are actually layers themselves. So in this case, we want a softmax, and actually a logarithmic softmax, which is what was used in the case of AlphaGo. So we will use that here. And I believe the log softmax. Yes, so we'll use this log softmax function. But basically what a softmax function does is it will just map this array of outputs, so 7 outputs in our case. We'll call this policy ls. It will map this array of 7 outputs to a value between 0 and 1, and all 7 values will add up to 1. So we basically have probabilities now. We're converting our outputs into probabilities of choosing this action, essentially. So if action 5 was the best action, you might see like 0.8 for action 5, and then the rest of the 6 outputs adding up to the last 20% or 0.2. But for this log softmax, we just need to specify this this dimension parameter, and this will be just which axis of the array are we computing the log softmax. In our case, it's just 1. The reason this is 1 and not 0 is because we have to consider our batch dimension. So there's always we're going to be passing more than one training sample at a time, which we can maybe explain that a bit later as well. But we're going to be passing more than one training sample at a time, so that will make up the 0th dimension, and our log softmax can then compute along dimension 1. So what we've done here, I believe I have a typo there. This should be policy. So what we've done so far, just to reiterate, I think this should also be bias true, and we can remove the padding, and kernel size 1. So in the paper they do mention that these were equivalent for the value and policy heads. So that is what we'll do here. But up to this point, basically we've now defined all of the layers that will eventually be in the network. So right now, if you called this an instance of this Connect4 model class, you have basically all of the layers that will be built into the network as attributes to the Connect4 model. But we don't have any sort of definition of connection, right? We put them in order here just for convenience, but right now, when we train the model, Torch does not know how to connect these things up, right? Do we do the initial comm first, and then do we jump down here? There's all these layers, and we need to actually now define how we want to traverse through them. So that will be what will be defined in this forward function. Basically, we want to pass this X array, which is going to be the state of the board at any given point, and we want to tell Torch how to pass that data, all the way from the initial convolutional layer out to both the value head and the policy head. But thanks for watching. Hope you enjoyed, and I'll see you guys in the next one.